Welcome to our September public lecture. Today, instead of an old professor, we've got two bright young postgraduate students who I think are giving their first public lecture. So I'm Matthew Bales. I'm from the ARC Centre of Excellence for Gravitational Wave Discovery, which is a national research centre. I'm also from the Swinburne Centre for Astrophysics and Supercomputing, and we have about 40 or 50 Ph.D. students undertaking their studies, and today you're going to hear from Jacob and Monse. Just before we begin, I'd like to respectfully acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional owners of this land, and pay my respects to their elders past and present. I'm not going to give the introduction to Jacob and Monse because they want to do it themselves. So at this point, I'll hand over to you two. Thanks. Welcome.
Good night, everyone. Yes, this is our first public lecture, but I think it's going to be okay. We have an hour to achieve a lot of goals. So we're going to start with Jacob. Jacob Askew. He's Australian. He's from Newcastle. And I just wanted to ask you, how did you end up doing this?
Yeah, well, I didn't always want to be an astrophysicist, but I really fell in love with it when I was in high school. And I was just doing some really simple experiments, and they really opened my eyes onto the possibilities of what you can do with astrophysics. And then I really fell in love when you can see in the top left, I visited a telescope, so a real-life, world-class radio telescope in New South Wales called ATCA. And Monse, how did you start your journey?
You can tell from my accent that I'm not from here. I'm actually from Chile. I don't know if you can see there, this. We intentionally put the world like this because technically Chile and Australia share a border in Antarctica. So technically, this is the closest view where you can see Chile and Australia. So I was born there. I did my undergrads in astronomy because even though I'm from far away, Chile is a really good place for doing astronomy. Chile has really beautiful, clear skies, almost as beautiful, like Australia has good night sky, but Chile have better ones. But it's the same sky because it's also the southern hemisphere. But that's allowed to a lot of telescopes to be installed in this country. So at least universities, they teach astronomy. So when I knew that they give astronomy courses, I just enrolled into that. I did my undergrads, then did a master's degree there, and then I crossed the ocean to get here and to do a PhD at Swinburne. So it's a long travel, a lot of years at this point. But yeah, growing up, I didn't know what a scientist was, really. It wasn't really like an option. You're always going to be like an engineer, a lawyer, or a physician, something like that. But when I realized that they actually did teach that at the university, I just did it because, like, why not? Why not to try? And yeah, I think that's pretty much. So we're going to start with something called Pulsars. What is that? I didn't know anything about that before I arrived to Swinburne, but here there's a bunch of scientists that work with Pulsars. And Jacob will start, and you have 20 minutes.
Awesome. Okay, so by the end of this talk, I hopefully will explain what a pulsar is and how amazing they are. But first, we're going to start with a few baby steps. So one of those experiments that I fell in love with when I was in undergrad was a really simple experiment. And it was just watching the motion of a pendulum swing on a mass. And this is something that you guys can do at home. You just need a stick, a rope, and a little rock to tie it to. And you can genuinely measure the acceleration of this planet that we live on. And you could do this experiment any number of times, and you might get some varied results. But they should coalesce with the truth or what we understand gravity to be. Right? So this is no different to the large experiments that we do, such as like a massive, large hadron collider in Europe, per se. It's got the same principles. We want to understand the fundamental properties of our universe, where in this case, we're looking at the beams of electrons as they pass by each other and smash, and we take a photo of that. And these two experiments, although one is quite simple, and the other one quite complex, they've got the same goals in mind. And this is one of the reasons why I fell in love with science. And then my love for astronomy comes because we can't truly understand the universe without looking at it. So what we want to do is we want to use world-class facilities to understand fundamental properties of our universe. And today I really want to tell you about pulsars, but I'm going to start with our solar system. So to give you a sense of scale, we've got the Earth, which is right there, and it's quite small compared to the other bodies in the solar system, in particular the Sun, which you'd have to put 100 Earths side to side and about 100 Earths top to bottom, meaning that it's got a volume of about 1 million Earths just to fill it. And something we're going to be talking a lot about throughout this talk is mass. And I want to contextualize the mass of other objects with our solar system. So we're going to talk a lot about one solar mass. So that's just the mass of our Sun. And it's more than 300,000 Earth masses to go into the Sun. So it's quite a large object. And how the Sun is one of 300 billion stars or so in our galaxy. And it's a pretty typical one. And the life cycle of a star starts in a cold, unperturbed body of gas called a nebula. And eventually this mass will accrete until it starts nuclear fusion, starts burning the hydrogen. And then that star will run out of hydrogen and start burning helium and swell up into a red giant. And this red giant is going to burn through its helium, just like the old star burns through its hydrogen over the course of millions of years. And at this point, our Sun would have enveloped some of the interior planets, and potentially us included. And then after it's finished all its hydrogens, all of its helium, it's going to implode into a planetary nebula and recycle a certain fraction of that gas out into the solar system that it was living in. And these objects, at their core, leave behind a relatively dense object called a white dwarf. And these objects we're going to be talking about later. But I want to talk about something interesting, which is a star that's up to around about 8 times the mass of our Sun. And these stars are more rare, but they often form in binary systems, and they're quite interesting because they burn bright and fast. So these stars are going to burn several times faster than a regular star, and they're going to burn hot blue. And these stars are going to swell up, once they've finished burning their hydrogen, into a super red giant. And these stars, when they collapse under their own gravity, are going to implode into a supernova explosion, which is much more spectacular. And why we care about this is because they too are leaving behind a compact object, but in this case, it's going to be a neutron star. So this neutron star, I want you to imagine, is about 1.4 times the mass of our Sun, but it's only the size of Melbourne CBD. So this is an incredibly dense object. And these are the subject of my study and interest. So as I show this animation of a supernova explosion, I want you to close your eyes after you've had a look at the pretty explosion, and then imagine a neutron star that's spinning rapidly. It's inherited the rotational energy of its parent star. So as you can imagine, as you pull your arms in, as the radius decreases, the star is going to inherit that mass, and it's going to spin. And if we're lucky that energy that it's producing out of its magnetic axis aligns with the Earth, then we see it as a pulsar rotating through interstellar space. So there's estimated to be about 1 million of these neutron stars throughout our galaxy, and we can see more than 3,000 of these objects as pulsars. And you can see the emission of radio waves arrives like a lighthouse passing across our vision as this pulse of radiation. And the way it's actually created is similar to something Monse is going to talk about, which is the relationship between a fast-moving object inside a magnetic field. So all of these pulsars, they keep their rotational energy, but they also keep the magnetic field of their parent star, or so we believe. And this magnetic field creates this amazing energy that emits through interstellar space. I want to talk about another effect. So now I've got a white dwarf orbiting around a neutron star that's emitting those pulses. And on the bottom of this sort of figure, I'm showing the warped space-time because these bodies are incredibly massive. The white dwarf is typically 0.3 or 0.5 solar masses. so times the mass of the sun, and the neutron star is 1.4. So you can see that it's bending it's curving space-time more significantly than the white dwarf. But interesting, as I said, these stars often form in binary systems, and as these stars dance around each other, the white dwarf is actually changing the radio frequency, the waves that we see emitting from the neutron star. And we're going to use this effect to understand aspects of the world around us and properties of gravity itself. So the way we do this is we have this predicted arrival time of our pulse. Before it even gets to the telescope, we've been observing it for tens of years, and we have this model of our pulsar. And what we want to do is we want to observe this pulsar and then see the difference between what we observe and the model that we predicted. That difference could have been the warping of space-time slowing down, making the radio waves take longer to reach planet Earth. And this is what we call a time of arrival, or the observed TOA. And we basically collect all of these timing residuals across time, and then we paint a picture with models about what we know about the properties of the neutron star binary and the properties of the object itself. And some fun facts about this is that there's all sorts of things going along line of sight. So I'm going to be talking about a few of those. But interestingly, this pulsar is spinning at hundreds of times per second sometimes, and we can predict when that pulse is going to arrive within an order of 100 nanoseconds. So that's an incredible level of precision, and this allows us to probe general relativity. So just to recap, I talked a lot about neutron stars, so let's just recap real quick. But basically, we're interested in these incredibly dense dead stars that are rapidly rotating and sending signals to us across interstellar space. And we want to understand properties of them because we can't do these experiments on Earth. If we could, we'd love to, but instead we have the privilege of looking through and observing these pulsars. And I want to go back to the solar system to talk about another effect that that was one of the methods used to prove Einstein's theories of general relativity. And it's the fact that the sun is massive enough that it actually perturbs Mercury's orbit. And it perturbs it by a very small amount, but a measurable amount. So I want to quantify that for you with this diagram where you can see in the bottom left, we've got this protractor of 90 degrees. If we take one of those degrees, we can split it up into 60 arc minutes. And then we can split up one of those 60 arc minutes into 60 arc seconds, and this is the level that we're measuring the variation in the orbit by, to be 43 arc seconds every century. So the mass of the sun is quite large and significant because it has this general relativistic effect, and you can see an animation of that effect if we were able to speed up by hundreds of years. And I want to bring this into context because the effects that we see with neutron stars are several orders of magnitude more significant, and we'll be exploring that in just a moment. So how do we actually measure general relativity when it comes to the neutron star system? So here I've got a very scientific graph of the mass of the pulsar is on the x-axis and the mass of the companion is on the y-axis. And you can imagine this pink line would move up and down. If I made that white dwarf more massive, I could turn it into a neutron star and then the bar would go up. If it just happened to be a little bit heavier, a little bit lighter, we would measure it to be so because it would be bending the radio waves more or less, depending on its mass. And this on its own is not a measurement, right? Because we can't measure the mass of the pulsar no matter how accurately we measure the mass of the companion. So we need a second curve. And this curve depends on the orbital orientation of that system. So you can imagine that if you had the radio waves coming directly at you and the white dwarf sort of eclipsed your view of the pulsar, then you would see a stronger gravitational effect. And if you had the pulsar orbiting, the white dwarf orbiting in a face-on, sort of like a pancake, then you would see less of an effect. So this blue line would move left or right or up or down. And the overlapping region is where we get our mass measurement of the pulsar and its companion. Now, this assumes general relativity to be correct, but to be able to do that, and we cannot, we can't use this to prove it on its own. However, if we get a third line and it all lines up in the same area on the graph, then we can test general relativity. So every additional perturbation of the orbit that is predicted by GR that we can measure adds another test to our tool belt. And this one actually, this ripples in space-time is due to the emission of gravitational waves as the binary orbit shrinks. So this is how we get even more precise mass measurements and how we get even more tests of general relativity. And I want to contextualize that with a really cool example, my favorite pulsar in the whole universe, maybe the best pulsar in the whole universe, which is the double pulsar, because there's two of them. And what you can do with this object is actually 7 independent tests of general relativity, because it's a highly relativistic system. So these two pulsars dance around each other every 2.5 hours or so. And the pulsars individually are sending signals hundreds of times per second. So we're getting a lot of information from this system, and it was discovered in early 2004. And since then, the secondary pulsar, Pulsar B, because it's so relativistic, even though these things are billions of years old, the Pulsar B's beam is actually processed out of the line of sight, and we no longer see it. And it's predicted to return within the next decade. So this is a highly dynamic system that we want to study, because we want to understand the properties of what makes up a neutron star and the properties of gravity itself. And to give context, to play back to the Mercury example, Mercury's precession is 43 arc seconds per century, and this system's precession is 17 degrees per year. So it's a significantly greater test of Einstein's theories. And again, we're going to go back to now a real plot showing you what I showed before, but the real data. And you can see that we've now got 7 overlapping tests of general relativity. And you can imagine if Einstein was wrong, one of these or many of these would be in different spaces all over the graph. For instance, if we just look at that pink curve, perhaps it would shift left, perhaps it would shift right. Okay? And then this is such a precise test of general relativity and such a precise mass measurement that we need 6 decimal places on the solar mass, and we need a zoom-in plot on the diagram to really show that overlapping region. And what you can see, to contextualize it, this is approximately 900,000 Earth masses in total, and we know the answer to its mass within half an Earth mass. So it's an incredibly precise mass measurement, and one of the best that we have. Now, there is a slight problem. So one of those tests of general relativity depends on how well we know the distance to this object. So this is where a bit of science comes into context, and I need to explain this graph. So on the x-axis, we've got the distance to the double pulsar system, and here I've got 2 distributions in blue and black. And both of these distributions are using quite robust techniques at measuring the distance to objects. It's very difficult, but these on their own are very good techniques, right? And then, although one is more precise than the other, we can't disentangle which one is correct because they're in disagreement. If we knew the distance precisely, it would just be a straight line straight up. And if we didn't know the distance, it would be more like a pool at the bottom, right? And if they agreed, then they would line up sort of like that. But unfortunately, we need a third independent test to sort of rule out or determine which method is correct at determining the distance. And for reference, on the x-axis, I've used parsecs, and 1,000 parsecs is about 1,000 light years. 3,000 light years. So it took the radio waves about 3,000 years to reach us from this object, which is kind of fun. What we're going to do to solve this problem is use a world-class radio telescope called Meerkat. So this is 64 antennae that are built in South Africa, and they're made up of, they're going to be a part of the SKA, which is going to be the world's biggest radio interferometer ever seen. And And these telescopes together detect signals, and then you determine the differences between them to make one signal. And basically, this to put it into context, this telescope is 7 times more sensitive than a 64-metre dish in Australia called Parkes or Moriang. And then what I'm going to do is we're going to use this telescope to look at the radio sky. So because pulsars are going to be emitting in the radio, and if you were able to look at the night sky in radio, this is what you'd probably see if you had really good vision, or meerkat-esque vision. And interestingly enough, there's lots of sources in our field, but pulsars are really, really tiny. Remember I said they were the size of a city. So they're very small point sources, and we're able to study them to an incredible level of precision. And for those that might already know what an active galactic nuclei is, Monse is going to talk about them, but you can see tons of them in this radio image. But we're getting ahead of ourselves, so I want to talk about some of the research that I've been doing as a PhD student. So to put you in the context of how I look at the radio sky, I want to take you to a hot summer's day by the pool that hopefully will be coming up in the coming months in Australia. And if you look at the bottom of a pool, you'll notice that all of these patterns sort of come and they go with time. And you'll notice like points are brighter than others. And this is because of the way that the light from our sun is interacting with the turbulent surface of the pool, and it's leaving behind a pattern. And that pattern, if you do some clever mathematics and do a bit of backtracking, can tell you about how that surface of water was moving. And this is directly analogous to what I do with radio. So replace the sun with a pulsar and replace the surface of the water with an interstellar soup of electrons, and replace the bottom of the pool with a radio telescope, and you've got exactly what I like to play with. So this is my data with of the double pulsar with frequency on the y-axis and time on the x-axis. So as we observe these pulsars across time, we notice that their pattern changes. So the pulsars are becoming brighter or they're becoming fainter. And this is because those radio waves, they're getting affected by things along line of sight, like another white dwarf or a neutron star in its system, but also it's got to pass through all of that interstellar gas and material before it reaches us. And interestingly enough, we're able to untangle the resultant picture, which you see here, by studying the correlations and the properties of the bright patches in yellow. And one thing that you'll notice is you'll be literally able to, in this image, see the motion of the double pulsar as it dances around its orbit in this image, where as the velocity of the pulsar is minimized, those islands of intensity are maximized. And as the pulsar velocity speeds up again as it's going around in its orbit, those are going to shrink again. And this is showing about half of an orbital period of the double pulsar. So you see it twice as it goes 1, 2 around the orbit. And what I've been able to do using this technique, just like imagine if I moved the pool closer to the sun or further, or if I moved the sun further away or closer to the Earth, you would see a different pattern on the bottom of your pool. The same thing occurs with your neutron star. So if I move my double pulsar really far away, or if I bring it closer to Earth, I'm going to see a completely different picture. So then mathematically, I'm able to, with a few assumptions I might add, I'm able to determine the distance to the double pulsar to a level of precision that's similar to that of the blue method. So in orange, I'm showing the work that I've been working on. And you can see that it lines up with one of those other distributions, which means that we're quite confident that that distribution was an accurate representation of the distance to this object. And then after all of that, we've solved a few things. So I'm going to walk you through some of the impacts from this. So one of the first things they did with the double pulsar, because it's 2 neutron stars, depending on how close or how far away it is, that tells you the expected rate of binary neutron star mergers in the whole universe. So with a bit of extrapolation, if you know that there's one object here, there's a double neutron star, and it's about that far away, and we see this many of them etc., you can extrapolate to how many binary neutron star mergers you'd predict to see in the universe. So not only are we improving the precision and the accuracy of these tests of gravity, but we're also helping other science that you might have heard of at LIGO detecting these gravitational wave mergers, or hopefully binary neutron star mergers. And we can also start to probe the interior, which not a lot is known about, of neutron stars, and try and untangle how matter acts at such large densities. So with that, and that exciting science, I'm going to pass over to Monse, and she's going to be telling you about some more exciting things happening in AGN land.
Perfect timing. Nice. Okay, that was a lot. But you are still awake? Are we still doing this? Yes? You can say yes? So, yes, nice, excellent. Cool. So, as I said before, did I say my name? My name is Montserrat Martinez. And I'm going to talk to you about a lot of stuff today, but we're going to break it down in 3 big steps, okay? So, the first, I want you to talk about other galaxies. So far, Jacob's been doing an amazing job explaining cool things that happen in our galaxy, but I want to... There? Okay, so I will lean. Sorry if this is not too formal. So yeah, Jacob's been talking about things that happen in our galaxy. Now I want to take you to other galaxies. I also want to talk about cool things that happen in these other galaxies. And I think this is the hardest one. We're going to try to learn how to travel back in time. So, first of all, we're going to start going back to a plot that Jacob already showed a couple of minutes ago, but I will give you a quick reminder because Jacob left some details behind in this explanation, but it's okay. He only had 20 minutes, so it's fine. So Jacob mentioned that when you have new stars that are about 8 times the mass of the sun, they will grow into a super red giant, and then they will explode in a supernovae. I want to highlight how powerful is a supernovae explosion. These explosions are so bright, yet you can see them from other galaxies. And actually, they're very useful to measure distance in the universe. But after this huge explosion, you can have a neutron star, but you can also have a black hole. A black hole, and Jacob already talked about general relativity. We live in a universe that has something called space-time. This is a fabric of the universe, and what a black hole is a deformation in space-time so deep that not even the thing that travels fastest in the universe, which is light, is able to escape. It's really hard to visualize this effect, but Jacob already talked about the sun. The sun creates a curvature in space-time, but light is actually fast enough to escape this potential whale that the mass of the sun is creating. But if you shrink the sun to a smaller radius, and this time I tried to use football fields, I didn't even bother try to put them all aligned, like all the 30 aligned, because it's impossible in just one slide. I tried to compare these scales. But this creates a potential well so deep in space-time that now light is no longer able to escape it. Okay? Cool. So now, I don't want to talk about black holes. I want to talk about something way cooler, which are supermassive black holes. Supermassive black holes are a thing. We're not really sure how they form, sadly, but this is work in progress. But when I say that these are massive objects, they are massive. You can fit in the supermassive black hole of the Milky Way 4 times 10 to the 6 solar masses. During the talk, I will talk about 10 to the 6, 10 to the 10th, 10 to the 11th, but I did the right, how much is that in millions? Sorry, I cannot make the conversion at this point. I'm very used to talk about 10 to the 6, 10 to the 7, so I will do the disclaimer underneath so you can read it. So imagine a place in space-time that is filled up with million solar masses. This is very massive and create a huge distortion in space-time. Nevertheless, these objects are actually not super big in radius. If you want to have a supermassive black hole like the one in the Milky Way, you only need 17 suns, one next to each other. So it's a really small region of space-time, but it's super, super massive. So I can say this in theory, but these are real things. If you took up your telescopes and look at the night sky, there you can see the Milky Way. If you look at the center of the Milky Way, this was the method that we used for so many years and was the closest thing that we can do to observe a supermassive black hole, which is actually look at the orbits of the stars going around the supermassive black hole. That red X is the place where the supermassive black hole should be. And even with calculating the orbit of these stars, we can calculate the mass of the supermassive black hole. But a few years ago, and here is when Jacob were talking about cool experiments, this is the coolest experiment. This is called the Event Horizon Telescope. This is a combination and a huge effort around the planet of combining a bunch of radio telescopes from different sites in the planet, and they all look at the same place at the same time. So what you achieve when you do that is that you can create a telescope the size of the planet. You cannot go bigger than that. This is the biggest telescope that you can create. So now we're actually able to take a picture of the supermassive black hole of the Milky Way, which is amazing. Imagine, we can look at it in a picture. So, of course, we are not alone in the universe. Our galaxy is not the only galaxy in the universe. 100 years ago, we thought it was, but now we know that there's a bunch of galaxies in the universe. And our galaxy is actually part of something that we call the local group of galaxies that I highlighted in a red circle. But there's also other galaxies and other groups of galaxies that we call galaxy clusters. And the closest one to us is the Virgo cluster. Why am I telling you this? Because in one of the galaxies of the Virgo cluster, M87, there's something cool happening. We have observations about this galaxy, and you can see there's this kind of like wobbly arm on this part. And when they used the Event Horizon Telescope, they were able to take a picture of the supermassive black hole of this galaxy. So this is way cooler. We can see a supermassive black hole from another galaxy that is in another galaxy cluster. So this is very far away and really fun science. So if you actually were paying attention and you've been listening about radio a lot so far, what is actually happening in this galaxy is something called active galactic nuclei. But I'm going to explain that a little bit more in the next slide. But I want you to, I've been intentionally saying that we find the supermassive black holes in the center of galaxies. We have the supermassive black hole in the center of our galaxy, and we've been consistently finding that all the supermassive black holes in other galaxies are also in the center, which is a really weird coincidence if you think about it, because as I mentioned before, the radius of a supermassive black hole is very small in comparison with a galaxy. So there's a relation that exists that is with the mass of the galaxy and the mass of the supermassive black hole. If you have a big galaxy, it will have a big a more massive supermassive black hole, and if you have a smaller galaxy or less massive galaxy, you will have a smaller supermassive black hole. If you try to look this into statistics, it's really unlikely for this to happen. It's kind of like saying that in every major city at the CBD, you will find a fat cat. And if the city is even bigger, then you will have a fatter cat in the center. So there's a lot of things happening here. We're still trying to find explanations for this, and we're going to talk about this a little bit further. So I've been talking about other galaxies, the Milky Way, but I haven't stopped to tell you what actually a galaxy is made of. So a quick recap. Most of the mass of a galaxy is actually made out of dark matter, which is about 85 to 90% of the mass of the galaxy. Then we have stars. Stars are only about 5 to 7% of the total mass of the galaxy, and then we have gas. Gas is really important for galaxies because you want your gas to be chill, as Jacob said before, because then you can create stars. If you cannot create stars, this will create issues into the galaxy, and we're going to call it in a few slides more something called quenching. In the center, you also have the supermassive black hole that is equivalent to the 0.001% of the mass of the galaxy. So cool, recap. We already talked about other galaxies, right? So now the next step is to talk about cool things happening in other galaxies. And this is a slide that I already showed, but what is happening here and what we see in these wobbly arms is an active galactic nuclei. What is happening here is that there's material, it could be gas, it could be stars, that are falling into the supermassive black hole. And imagine how that interaction is. Imagine a star falling into a supermassive black hole. This is a super powerful and energetic phenomena happening in the galaxy. So all this energy create these arms that are actually jets, which is actually look kind of like what Jacob showed before, which is a pulsar. So you have a structure in an AGN. You have the supermassive black hole in the center. You have an accretion disk that is all the material that is going into it. And then you have something called a dusty torus, which is just dust that accumulates around the accretion disk. And then you have these powerful jets. So now, we've been talking about radio, we've been talking about taking picture of the sky, but we haven't really explained much about light, and we're going to need it to go to the next step. So we all know, or probably I hope we all know, that the lights behave like a wave, which means that you can have longer wavelength and shorter wavelength. The portion of light that we can observe is very limited. It's highlighted there with the rainbow. So when we observe a galaxy like AIM-87 with just regular telescope, we see this. When we look at them at longer wavelength, which are the ones that the radio measure, you will be able to see the jets. And if you look at the galaxy in X-rays, you will be able to see the gas and the dust glowing. So if you add up all together, you will end up with this final version of the galaxy, and then you have all the information and tools to understand what is happening in galaxies. Now, having an AGN in your galaxy is not good news, because this is a very powerful event happening in your galaxy. So one thing that can happen, for example, is that the jets are so powerful that can blow away all the gas that you have in the galaxy. And we already said that we need the gas in order to create stars. If your galaxy don't create stars anymore, it will be slowly dying. Also, all these magnetic fields that are around the supermassive black hole also will be creating a very powerful energy, and will heat up the gas surrounded in the galaxy. And again, if your gas is heat up, it cannot cool and create stars. So AGNs are really bad for galaxies in terms if you want to have a really young galaxy forever. Now we talk about galaxies. We talk about cool things happening in galaxies called AGNs. Now we're going for the part of trying to travel back in time. So as I was explaining before, we all know that the universe was created in a Big Bang, right? After the Big Bang, the big explosion, you have a period where everything just grew super fast, that we call inflation. Then you have a universe big enough so light can escape from this really compressed gooey soup of stuff that is created in the universe. And you can have the CMB image. And then you go through a fuzzy universe that is full of hydrogen in neutral state that will make something called the dark ages because it's very foggy and the light cannot really escape anywhere. So when things start actually happening is after about 0.2 billion years after the creation of the universe, and that is when we start to see the first stars that are being formed and the first galaxies. So this is where all the action is happening up to like 4 billion years, then everything just evolves more naturally. But we need to remember that the universe is expanding, but when I say expanding, it's growing, and it's growing in an accelerated manner. So this scale is actually logarithmic. So when you have a universe that is expanding and you have galaxies on it, something called cosmological redshift will happen, because these galaxies will start moving away from each other, but not because they are actually moving, it's because space is being created in between them, and that will affect how we see the light from these galaxies. This stretching of space-time will create this effect where all the information from the galaxy that comes from the light will go to the red, to longer wavelengths. So, for example, if you see a galaxy that is 8 billion, when the universe was 8 billion years ago, you will see that all the information from the galaxy will be shifted a little bit to the red. So now we can use this as a tool to measure not only distances, but when this galaxy was observed, in which stage of the universe. So when we are looking at these galaxies, and I will call it, for example, redshift 1, you are seeing this galaxy how it was when the universe was this specific time and this specific big. So this is where it's very useful for astronomers, and we don't really talk about billion or years, we talk about redshift, because it's easier. Because when we look at and observe and try to analyze the light from a galaxy, what a telescope is doing is like exactly what is doing this, this triangle, that you are using a prism with a spectrograph to move to decompose the light coming from the galaxy in different wavelengths in the spectrum that we see here. And all these spikes that you can see, that is the useful information that what we astronomers want, because this can tell us the age of the galaxy, the mass of the galaxy, if there's stars forming in this galaxy, if there's an AGN in this galaxy. We have studied and we know a lot about these patterns, but the issue, as I said before, is that this will be shifting with redshift. So if you look at these spikes, as you go up in redshift, they go to the infrared to at some point that we are not able to detect them, for example, from the ground. And actually, all that we can observe from the ground is up to redshift 4, maybe 5 or 6, but it's just after everything cool in the universe already happened, which is a bit concerning because we are extrapolating the entire history of the universe, extrapolating just from here to the present. So this is why telescopes like the JWST are so relevant, because when you want to observe infrared light, one of the major issues to observe them from the ground is the radiation that the sun emits. So not only JWST is bigger than the previous one, Space Telescope Hubble, it looks into the infrared and is very far away from Earth, and actually have a shield that protects it, the detectors in the telescope from the light of the sun. So now JWST expand all our capability to study the universe, and actually now we are able to look at the cool part of the universe, when everything is happening, when the stars are forming, when the galaxies are forming. So, cool. We look at galaxies, we look at cool things in galaxies, and now we know how to travel back in time. So if you understood anything that I say until now, this was worth it. Like, the rest is nothing. Because now we're going to Ph.D. territory, and this is what I've been doing these years here at Swinburne. And it all started with these galaxies that are called massive quiescent galaxies. Massive, again, massive as the Milky Way, 10 to the 10 solar masses, 10 to the 11 solar masses, or I don't know how to say the number. This object looks like red circles in the sky. And here I want to clarify again what quiescent means. This means that these galaxies are not longer forming stars. That's why they look red. So we study these galaxies because there's an issue. You find these galaxies when the universe was only 1.5 or 2 giga-years old. So this means that you have a galaxy with the mass of the Milky Way, but very early in the universe. And our models struggle to make a good model to predict that these galaxies exist. So one of the issues is that is too massive, and also we find too many of them. So my first job at the PhD was actually observe AGNs. At the time, we didn't know they were AGNs. We thought that these were massive quiescent galaxies. And what I'm showing to you here is the spectra. This is a real spectra, but it's observed from the ground, which means that I only get up to 2.3 microns, which is really short. And I can barely see some structures in the spectra, which made it tricky. But spoiler alert, all of them were AGNs. So this was the first time that we have a large sample to analyze AGNs in this slice of the universe. And what we find is if we take the numbers of AGNs and divide it by the number of galaxies in this period of time, the fraction of these galaxies is super high, about 80%. So we have massive quiescent galaxies between redshift 3 and 4 when the universe was 1.5 or 2 giga-years old. We don't know how they are quiescent, but we also see a lot of AGNs. So these smell dodgy. But one way to settle this is to actually use the JWST telescope. And we can observe, now you can see the difference between the spectra. The one from the above was from the ground, which is really noisy. I can see only a few spikes. Well, JWST give me up to 5 microns to observe. So now I have all the tools that I needed to properly analyze these galaxies. And what we're trying to publish now is that, in effect, the number of AGNs in this slice of time is influencing in these massive galaxies and influencing them to be quiescent. So this is what I've been doing these last 3 years. But this is not the end. JWST have brought a lot of new discoveries because, as I said before, we can now actually look back where everything is happening. I don't know if you have heard something called little red dots, which are also massive galaxies, but found at even higher redshift 7, for example. These are real researchers that actually work at Swinburne. that have been finding these objects. And also we have other issues because we can also find massive galaxies at redshifts insane, like redshift 14. This means that the universe was 0.3 gigayears old, was nothing. And that was also found by a researcher here at Swinburne. So there's a lot of things that JWST is showing that maybe our theories are a bit wrong. But what's next? JWST still have one issue. You can only point a very small space in the sky. So the Nancy Grace Roman telescope, named after this amazing scientist that was in charge of creating the first space telescope, the Hubble telescope. And they named the telescope after her because now this telescope will be able to observe a wide area of the sky. So now we will have more data, more numbers, and more stuff to make up how the universe actually was created. So that's it from me. Thank you.
Questions?
Yeah, the thanks has to happen at some point.
So
Yeah.
thanks very much for that insight
Yeah,
into a couple of real PhDs here at Swinburne. We've got some time for questions. Unfortunately, our roving microphone's not working, so if you want to ask a question, you have to put up your hand and I'll get you to speak loudly. We have one volunteer here.
Simple sounding question, but I suspect it doesn't have a simple answer. But it's always been possible to parallel a spinning neutron star has a magnetic field at all, and what the source of that magnetic field is, considering that spinning neutrons, you wouldn't expect them to have a magnetic field.
The question was, how can a neutron star have a magnetic field at all? And I'm going to put Jacob on the spot and answer it. And if he can't, there's an expert here, I believe, on pulsars that might step in.
Yeah, so I think this is still, I think it's one of the, I think it's actually one of the well-known things about pulsars. There's still a lot of mysteries, but basically every star has its own magnetic field, and then as the gravitational collapse occurs in the supernova, that magnetic field is sort of shrunk and therefore increases in strength. And when we look at young pulsars, or pulsars we believe to be young, because they're close to their supernova shell, we find that they have incredibly high magnetic field strengths, so 2 or 3 times greater than those even in AGN around pulsars. Anything to add, Matthew?
Yeah, thanks, Jacob. Although they're called neutron stars, in the core they have superconducting protons which can carry currents, and currents can carry or generate magnetic fields. About 5% of the neutrons are superconducting protons. Okay, next volunteer.
Just want to go back to 200 million years after the Big Bang, where you said stars were starting to form. How do we know that information is true, considering that we did not have, say, JWST, and even, I don't know, Hubble could pick it up? What evidence do we have that that period, say, was the beginning of stars and so forth?
Yeah, that's something. Oh, yeah. The question was how we can know that when the universe was 0.2 gigayears old, you actually start creating stars and galaxies, right? Cool.
You said 200 million years old.
200 million years old. Yeah, I don't know how to compare the numbers, sorry. Well, even though it's true that we were not able to observe that before, what we do have is something called a cosmological model. The cosmological model is being proven right so far. There's a bit of a tension at the moment, but the main experiment that astronomers use to measure the parameters of this cosmological model was actually measuring distance with supernovae. So when you are able to know when this explosion happened, you can calculate distances. And with this, you can get really farther back in time. And also you need to constrain other parameters from this cosmological model, like the density of stars that you have in your period of time, and then you can trace it back. So it's just, if you formulate a cosmological model, you will have some tests to do. But these tests are independent of you can actually observe this period of time. So, for example, a couple of months ago, there was one paper released that you find a galaxy way too early in the universe, and they redo the calculation of the cosmological model, and they say, oh, maybe the universe is twice the age that it is now. So these things can vary when you have more information, but it's basically all based in this cosmological model. You also have the CMB, which is the first light when the light was able to escape. So when you study the CMB and you have all these measurements of distance, you can start adjusting this cosmological model.
But we can't say that star over there is 0.2 billion years.
Actually, at the moment, these stars are still theoretical because we haven't observed one yet. There are some claims that JWST actually observed one, but there's a paper that is being a bit polemic at the moment, because this is what we call POP3 stars. The population of stars that we have now is POP1, that the ones that were previous to us, it was POP2, and that's the only thing that we've been able to detect so far. So the first stars that probably are super massive, we still haven't been able to observe them. Maybe we did. It's still in discussion.
We have another gentleman over here, and you don't have to be male and old to ask a question. So
hopefully everyone can hear me. So I assume the James Webb Telescope sort of changed everything in regard to AGNs and pulsars, but is there anything else you can tell us that's been found out that's around the edges sort of both of your PhDs? Any other interesting things that it's found, relevant to that, that's surprising?
I have one. The question was, is there more interesting things that JWST is showing so far? Yep. So for example, I told you that there was a relationship between the supermassive black hole mass and the mass of the galaxy. Well, the supermassive black hole measurements that we're taking now from galaxies at redshift 7 or 8 show that these supermassive black holes are way too massive for being created so far at that point of the universe. So the way that we believe like supermassive black holes grow is like they merge with other supermassive black holes. But with the detections that we have, they tell us that there's not enough time to have merged all of these supermassive black holes to make a supermassive black hole this big. So one of the theories, for example, to explain that is that dark matter, for example, can just collapse by itself. And then you create a supermassive black hole. And maybe you need to have a supermassive black hole in order to create a galaxy. We don't know, we're not really sure now which comes first, the galaxy or the supermassive black hole. So that's one thing that JWST is showing. And the other one is exoplanets. Like, so many exoplanets are being observed at the moment. There's a lot of publications happening at the time because kind of like the people from Exoplanet have issues with the observations at the beginning of the JWST because the instruments end up being too good for the observations. So everything that they got, they have to replan it again. So now in this third cycle of the JWST observation, they're actually getting good data and they're publishing their discoveries.
yeah, because the JWST is so large compared to any other space telescope, it's like a 6 meter instead of a 2 meter. It has much better resolution. And it's also above the atmosphere, and it also works in the infrared. And Ivo Larbi, who was on one of those slides, who works here and uses the telescope a lot, told me for many fields of science, it's literally 1 million times more powerful than any instrument they've been able to use before. And as Monse said, one of the things it's found is that these supermassive black holes are occurring a lot earlier in the universe than we had thought. All right, we've got 2 remaining questions and 1 remaining minute. Go!
I have a question in 2 parts.
Uh-oh.
One is related to the cosmological which you've mentioned earlier. Now, you've mentioned that this may mean that the universe is older. The other conclusion we might draw that the actual processes happened a lot faster, and it doesn't actually alter the. I'd like to comment about that. In conjunction with that, you also mentioned the supermassive black holes. One of the earlier theories was that a massive cloud would rotate very slowly, not fast enough to maintain its momentum, and because of that, the gravity combined with the dark matter would have collapsed it into a black hole. Can you comment on these two?
I'm going to throw to Mons on that one. You might want to briefly summarize the question.
Yeah, so there were 2 questions. One was about the cosmological model, if one of the explanations could be that everything is actually happening faster. I'm not an expert in cosmological models. I have friends that work in that. One of the really cool experiments that are happening right now is called DESI, which is a telescope that is basically mapping dark matter and how it's distributed in the universe. If we can constrain that, we can actually have a better insight in how the universe is actually growing. So it could be faster, but we're measuring it. So that could be an option. And the second one was about supermassive black holes, because one way to create them is just have a cloud of hydrogen, and then it will collapse into a supermassive black hole. But in between, there has to be steps, like some of the theories said that you need to have a star first, and then when this star explodes, actually collapse into a supermassive black hole. You also have black hole seeds, or something that we call primordial black holes. That is also an option that you have. When the universe was created, you have primordial black holes, and they start gathering together and create a supermassive black hole. But so far, all of these theories don't explain the observations that we see with JWST, although observations with JWST also need to be revised, because some of these results are just from photometry, for example, which is not ideal because you have other powerful instruments like the spectrographs, and you can take spectra of these galaxies to actually make sure that this information is 100% true.
Yeah, I think the age of the universe is pretty secure, but it's quite a perceptive question about how fast some processes take place, and forming a supermassive black hole from what's basically a gigantic star, like 1 million solar masses, is an interesting option that astrophysicists are looking at the moment. All right, we have one last question from the man in the striped shirt.
My question is to the first speaker. Your research was quite a third independent way of measuring distance to certain galaxies. Have you fixed the flaws in the cosmological distance ladder?
I personally, the question was, my research was looking at the distance to a pulsar, and then have I been looking at the distances in terms of cosmological distances? The answer is no. I've just been looking at this pulsar. The cosmological distances are working in a totally different regime, but I don't know how to, other than that, yeah.
Let me rescue you. Whilst it's true that Jacob's Ph.D. is, whilst very accomplished, it's measuring the distance to stars in our galaxy, not to stars in other galaxies. But if you look at the way neutron stars merge and the amplitude of the gravitational waves we get from that, you can use that to fix the distance model, and that's one of the objectives of our Centre of Excellence, OzGrav. So at that point, I might throw to wild applause for our 2 speakers today. Hold on. And we're going to have another public lecture, I think, on the first Friday of the next month. So I'd like to see you there. Thank you.